focus on the f-test and add to the statistical tools that we have at our disposal. So the f-test follows a new distribution to us, an f-distribution. We've covered a variety of other distributions, and this f-distribution is just another one of the probability distributions we can use to test our data against. And so far we've learned how to test the means of populations against one another using t-tests, but also at times we're interested in comparing the variances of populations to determine if they're equal or unequal. And importantly, as we move forward in some more complex statistical analyses, we're going to be using the f-test as the framework to do so. So this is going to be an important lecture for us to understand how this f-test rather works, so that way we are prepared moving forward for the next set of topics. So the f-distribution is a continuous probability distribution, but it's a little bit different than our t-distribution, that it's defined not by 1 degree of freedom, but by 2 different degrees of freedom, d1 and d2. And we can look at the curves on the bottom right here, and we notice that some of these curves tend to be quite skewed when our degrees of freedom for either one or both samples is quite low. But when both of our degrees of freedom tend to be relatively high, our distribution tends to resemble that of a normal distribution, which is what we're aiming for. So again, the f-test is designed to test if 2 variances are equal, and it does so by comparing the ratio of the 2 different variances for our samples. And again, our variance is based on our sum of squares, and we'll be comparing the 2 variances of interest for our particular test. And so our null hypothesis for this particular test is that the 2 variances are equal. And if they are equal, then the ratio of these 2 will equal 1. And this is in turn what we're testing against. And when we start to conduct the f-test, one thing that you'll notice is that the f-test statistic will never be less than 1. And so as we start to move further and further away from 1, the f-test statistic gets larger, then it's more likely that we're going to reject our null hypothesis. Now, a couple important assumptions for the f-test. The populations that we're sampling from are normal. In our particular course, we're going to assume this is true unless we're told otherwise. And the samples need to be independent of one another. So nothing new here. So again, for our f-test, our null hypothesis is that our 2 variances are equal. Our alternative hypothesis is that the 2 variances of the populations are not equal. So there's some type of statistical difference here. And our f statistic, again, is going to be the ratio of the 2 variances, and it's going to be the larger sample variance divided by the smaller sample variance. And we can test our null hypothesis at various significance levels. In this particular class, we're going to focus on a significance level of 0.05, but you should also feel comfortable doing so at a significance level of 0.01. And in this lecture, we're going to go through several examples to get comfortable doing so, and we'll also do so in lecture. Now, like our t-test, the f-test has its own statistical table. In this particular case, we've got a table for a significance level of 0.05 and a significance level of 0.01. Within the center of our tables, we have our critical values. This is the same as our chi-square table and our t-tables, just different values. And then in the first row, we have the degrees of freedom for the sample with the larger variance. Now, it's going to be key to understanding which of our samples is our numerator and which is our denominator, and so that's why we're going to go through several examples for practice. Because the first column will be the degrees of freedom for the sample with the smaller variance, or the denominator. Here we have another F table, this one specifically for significance level of 0.05. But importantly, the structure of the table doesn't change. The inner portion of it are critical values that we need to exceed in order to reject our null hypothesis. The top row are degrees of freedom for our numerator, outlined here very clearly in the table itself. And then this first column are the degrees of freedom for the denominator. I like using this table just because it's very clear in which numbers are supposed to be used. So let's go through some examples to see how this F-test works. Let's say that we are looking at the lengths of different red drum across the eastern and western Gulf of Mexico. We want to know if their variances are equal or not because we're interested in conducting a two-sample t-test, but we're not sure which of those t-tests we're supposed to be using. So in order to do so, we need to conduct an F-test. So our null hypothesis is that the two variances will be equal, and again our alternative hypothesis is that these variances are not equal. And for this example, we'll set the significance level at 0.05. So here we have our formula for calculating our test statistic. Now it looks complicated because of the long subscripts, but it's much simpler than it appears. The F value is simply the variance of the sample with the larger variance over the variance of the sample with the smaller variance. And then we need to define the degrees of freedom for both the numerator and the denominator. Now, at this point, we're comfortable, hopefully, with calculating variance and standard deviations. But at this point, also, I feel comfortable that you know how to do this. And so you're most likely going to be given the variances in any type of word problem that you need to solve for. So let's say that for our red drum, we have our associated variances here, and we need to identify which of these variances is larger, which is smaller. In this example, it's quite clear that sample 2 has a much larger variance than does sample 1, and so we'll place the variance for sample 2 in the numerator, the variance for sample 1 in the denominator. And this will then allow us to calculate our test statistic, 4.84. Now, similar to the t-tests, we're then going to compare our F value to the critical values in the F table. But before we do so, we need to figure out what the critical value is, and this is going to be determined based on the degrees of freedom for both the numerator and the denominator. So we'll go back here, and we need to know how to calculate degrees of freedom. Well, it's the same as it is for the t-test, except we need to do so for each one of our samples. So it's going to be n minus 1. And then we need to make sure that we are arranging the numerator and the denominator appropriately. Now, in this particular case, our two samples have the exact same sample size, so the degrees of freedom are going to be equal. So it's not important in this case which way we're assigning things because it's equal. But as we move forward in the next two examples after this, we're going to see that it's important to keep track of which sample is the numerator and which sample is the denominator. So our two degrees of freedom are going to be 19 for this particular example. So we have our test statistic of 4.84, and then we need to find our degrees of freedom on our respective table, both in the first row and in the first column. Now, for the first column, for the degrees of freedom for the denominator, we have a whole number here, 19. For the numerator, we have our range. We don't have a specific number for 19, but don't let this get you discouraged. What we'll need to do is identify the range of critical values that this could be, and then we'll use this to compare to our test statistic. And you won't have a situation in which the test statistic is so close in this particular class that you'll be unsure if it exceeds or does not exceed the critical value. So what we see here is that the F critical value is between 2.16 and 2.23. We can see that our test statistic, our F value, is much greater than this, 4.84, and so in turn we reject the null hypothesis and we can conclude that the variances of these two populations are not equal. Okay, let's go through another example here. Say that we're looking at the body condition of the sea turtles. We look at their plastrons, and we can then determine how either healthy or unhealthy they are based on their diets and their activity levels. And we're interested in comparing turtles in the Gulf of Mexico and the greater Atlantic Ocean to see if there's any kind of differences, and in turn if we need to adjust management for these turtles. So we are given some sample sizes and some variances for our respective regions. So we have sample size of 31 and 25. And so in this particular case, because the sample sizes are different, it's going to be important to keep track of which sample is the numerator and which is the denominator. And then we're also given the variances for these two regions. And so again, with our F-test, our null hypothesis is that these two variances are equal. Our alternative hypothesis is that our two variances are not equal. And we'll use 0.05 for our significance level again. So we go to our formula for our f-test, and we need to identify which of these particular variances is larger and which is smaller. Sample 2 has the larger variance, and so this will be our numerator. So we can fill this into a bit more simplified f test statistic formula here. So we can put these two variances into our formula and calculate out our f test statistic, 2.5. Now, here's where things come into play. We need to make sure that we identify the degrees of freedom for the numerator and the denominator appropriately, because that's going to affect the critical value that we get in our respective F table. So in this particular case, our larger variance is 30. So this is our numerator. So this will be the numerator degrees of freedom. So this is going to be based on sample size of 21. And then our other sample, sample 1, will inform our degrees of freedom for the denominator. So we can fill these in, so that way we can keep track of our degrees of freedom. Again, remembering that the degrees of freedom for each sample is n minus 1. We can then go to our table. Again, this table is the one I prefer because it identifies the numerator and the denominator in the table itself. We can then find our degrees of freedom on the respective table. Again, not over worrying if our values don't perfectly match up with those in the table, because we won't have a test statistic that will be too terribly close that will be unable to determine if it's significantly different or not. And what we find here is that the critical value for our particular distribution is between 1.88 and 1.93. We know that our test statistic of 2.5 is greater than this, so we can reject the null hypothesis. The variances between the Gulf of Mexico and the greater Atlantic Ocean are not equal for this particular example. Now, an important check to make when you are conducting this f-test is that your f value should always be either equal to or greater than 1. And the reason for this is that the larger variance is always in the numerator. So if you're getting an f value that's lower than 1, you know that you've swapped the numerator and the denominator. And so you want to start back from the beginning and make sure that you identify which variance is larger, which is smaller, and place them in the appropriate locations for the formula. Okay, one more example here, and what we'll do is have you pause the video and work on this on your own using the formula for the f value, and you can either go back through the PowerPoint, through the video, or go to your book and use the f table. Okay, hopefully you've taken a moment and worked through to calculate the F test statistic and calculated or determined the critical value, and then identified if we should either reject or fail to reject the null hypothesis. So, say that we're studying dolphins and pilot whales. We're looking at their microbiome diversity. We want to know if their variability in this biodiversity in their guts is the same or if it's different. And so we've got 32 dolphins and 21 whales in which to compare this with. So from this particular word problem, we need to identify our sample sizes and our variances. It doesn't matter which we identify as population or sample 1 versus 2. It just makes sure that we're being consistent in keeping the variances and the sample sizes together. One other thing that you're going to notice is that generally when we have a higher sample size, we're going to have a lower variance. And this isn't always the case, but oftentimes this is what we observe. And this is the case in the previous examples as well as this. Again, our null hypothesis for the f-test is that our two variances are equal, and the alternative hypothesis is that they are not equal. We'll test this again at a significance level of 0.05. This is our default. We've got our f test statistic formula here. We identify which of our variances is larger and which is smaller. We then can simplify this formula and then fill in the values to calculate our f test statistic. We then need to go through and identify the degrees of freedom for the numerator and the denominator based on the sample size minus 1. We can go ahead and do so. We then go to our F table. We find our critical value, or the range of the critical values, based on the degrees of freedom for the numerator and the denominator. And then what we find is that our F test statistic is less than the F critical value, meaning that we don't have enough support to reject the null hypothesis and that the variances aren't statistically different. Again, this third example we went through quickly. If we went through too quickly, go back through, try the example again on your own and see if your answers match up with that in the lecture. So at this point, we've got a variety of different statistical tests in our toolbox, and we're going to keep adding to this. But one important thing for us to keep in mind is that even though your exams are not comprehensive, you're going to be expected to understand when to use particular statistical tests. So you can use this slide as a guide to get a general understanding of when to use specific tests. And this is going to be important because we're going to continue moving forward in this course with more statistical tests, and this will be valuable for you moving forward in your career. And so the next statistical test that we are going to address in the course in the next set of videos will be the analysis of variance.